Thanks. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for the weekend just completed. I just thank you for these students, Lord. We thank you for calculus, the joy of doing calculus. I just pray you be with us this morning. Help us to glorify you, Lord, what we do. We thank you, Lord, that we're saved by grace if we accept it. And that it's not from our own works, Lord, but yours. In my prayer, Lord Jesus. Amen. Well, technically I'm supposed to collect the homework right now, but I'm going to give you guys one more day. And in tune with that, I will accept homework questions for about the first 10 minutes. So do you have any? Yes, sir.
44 on 8.4.
Let me steal your book. I forgot to get mine. Number 44 and 8.4? Oh, sorry, wrong 8.4. Oh. I mean, I'll just get you started here, but all you got to do to find the area of this. Okay, of course, this is y is equal to the square root of r squared minus x squared for a given constant r. So what you got to do is figure out what this is, figure out what that is.
Don't you have to factor in h to that equation?
Yeah, I'm not done yet. And then this, of course, is h. And so you'd integrate. So if you look at a typical infinitesimal area, dA would be y minus h dx. And that's going to be true from a to b. So you can integrate from a to b of the square root of r squared minus x squared minus h dx, and that should give you the area. And you see why it's in the trig substitution section, because that integral meets its demise with trig substitution. Yep.
So if you're wanting us to find a and b, are you wanting us to rewrite a and b?
I want you to simplify this integral as cleanly as you can. It may not be that clean. But yeah, you want to find a and b in terms of the given constants h and r. That's all I have to say about that one. Other questions? Yes, sir.
4 on the hyperbolic substitution.
Remind me which one. Can you just tell me the integral? Okay. And you're supposed to use a hyperbolic substitution, right? Okay. I guess my first move would be to figure out what kind of quadratic this is, right? So you completed the square. What happened?
It was x plus 3 squared
Minus 4? All right, so we're looking to make this like stuff squared, right? And what do we got to work with? We got ourselves cos squared phi minus sinh squared phi is equal to 1, right? Let's see here. What else do we have? Oh, so if I divide this by cos squared, what do I get? Now, let's see. If I divide this by sinh squared, what do I get? I get coth squared phi minus 1. So it looks like you might try out based on this. So I take this, I multiply this by 4, and I get 4 coth squared minus 4 is equal to 4 hyperbolic cosecant squared phi. So in view of this, I think what I would try would be an x plus 3 equals to twice the hyperbolic cotangent of phi. I might try that substitution. Because that will make the thing inside the radical become what? That will make x plus 3 squared minus 4 equal to Yeah. What would the dx be? I think it's -2. Right.
Could you make it x plus 3? Could you make that equal 2 secant theta as well?
I said to use a hyperbolic substitution though. So yeah. Yeah, if we were using a trigonometric substitution, we would, I think you're right, make a secant substitution. Anyway, that's the starting point. Is that a good start? Or what integral and hyperbolic functions are you going to face? Looks to me like you got yourself a hyperbolic cosecant squared over hyperbolic cosecant to the 5th with some number. So that's 1 over, if I see this right, the integral is essentially like 1 over the hyperbolic cosecant cubed phi, which is really just what? Right, which is just this. So, and how would you do an integral? How would you integrate sinh cubed phi, by the way? Okay, yeah. And then we can trade the sinh squared for cos squared, right? Because cos squared phi minus sinh squared phi is 1. See, so sinh squared is the integral of cos squared phi minus 1. And see, there you go. You're off to the races there. I mean, that's you make a u equals cos substitution. You're done. So it looks scarier than it is. Once you do the algebra after the hyperbolic substitution, it's actually not that bad. Anyway, I have left plenty of details for you guys to put together, but there's some hints. Other question? I'm sorry? The 2? Here? Oh, I'm not trying to say exactly what it is. I'm not going to simplify it. That's up to you guys. I mean, it goes to something like that. Now, I mean, this 2 is precise. That's there because that 2 is there. But I'm not telling you that the integral is this. In fact, I haven't written an integral. I haven't written d phi. I'm just trying to give you a sense of where you're going and that it's not impossible because you can do this integral. That's all. Other questions? Mm-hmm.
Number 48, 8.4.
So you're supposed to find the volume of a torus what was its equation? It's sort of obtaining it as a solid of revolution, right? So I think it's like out here somewhere, right? So this is at b, right? And this is x minus b quantity squared plus y squared equals to a squared, right? Now here a and b are assumed to be positive constants. Then you're going to take that thing and you're going to revolve it around the y-axis. And so this is actually the given curve. And then the solid of revolution is obtained by rotating this thing around the y-axis. So like, and then it comes back over here. something like that, right? And it says to use the method of shells. So what you want to do is to chop it into cylindrical shells. Typical cylindrical shell, something like this. I mean, here's the intersection of the cylindrical shell with the donut. All right, so the thickness of the shell is what? It's dx. What's the radius? It's x, right? So what's the infinitesimal volume of this little cylindrical shell? It's 2 pi x times this distance, right? Which is what? We call it h. And then dx, right? That gives me the volume of a particular typical shell. But h is not an innocent bystander. H depends on what? Although I can say this. This is for what? This is for b minus a less than or equal to x less than or equal to b plus a, right? That's going from here over to there. What is h? Right, h is equal to 2y. So that's actually 4 pi x times the square root of a squared minus x minus b quantity squared dx. See, because y is twice the height, it's twice the y coordinate there. Taking the positive solution up here, this branch of the circle, this part of it, this semicircle, I mean semicircle, we can solve. That's y is equal to the square root of a squared minus x minus b quantity squared. And you just have to integrate that. So just integrate that from b minus a to b plus a, and that ought to do it. It makes sense if you think about the endpoints here. What happens when you put x equals to b minus a or b plus a? You get a squared minus what? B plus a. You either get a plus or minus a on the endpoints in this squared term, which means you get a squared minus a squared. In other words, h is equal to 0 at the endpoints. That's a good check on our setup, right? These shells should shrink to 0 height on the edges of the integration region. That happens. So, and then you just have to integrate that. May I recommend I think we're going to make a x minus b equals to a sine theta substitution here. It's like the first trig substitution we did. It's a number squared minus the variable squared. So we make a sine substitution. Other questions? Again, if you're rusty on the shells, you can go back and read section 6.3. It's just weird to see people walking outside the window here on the 4th floor. You know, it's not right. There's still snow out there. Yep. Any other questions? All right, well, I'll collect it tomorrow at the start of class. So that brings us back to our favorite new thing, the partial fraction substitution, partial fractions technique, right? So I'll start us out here with a pretty easy example. Let's try to integrate dx over x squared plus, let's see here, 5x plus 6. Now, I suppose you could justly complain that we already know how to do this integral by completing the square and maybe an inverse hyperbolic tangent. But I'm going to show you this is an equivalent solution technique. Will give us an answer in terms of natural logs, which you guys maybe would like more. But OK, so basically the deal is here. I want to decompose this into basic rational functions. So x squared plus 5x plus 6 factors how? How about x plus 3 times x plus 2? Am I right? OK, so the partial fractions decomposition here looks like a over x plus 3 plus b over x plus 2. That's the partial fractions decomposition for this problem. Now I've got to do algebra to figure out what these undetermined coefficients a and b are. So my next step is to multiply both sides by the denominator. 1 then is equal to a times what? A times x plus 2 plus b times x plus 3, because the x plus 2 cancels, the x plus 3 cancels with the a term, the x plus 2 cancels with the b term. And then the simplest way to make the algebra go on these is just to plug in the zeros for this problem. So like if I put x equals to minus 2, or if I put x equals to minus 3, I get really nice equations. I get what? I get 1 equals what? For minus 2, this is gone. 1 equals b, right? For minus 3, what do I get? Well, the b term is gone. I get minus a, right? So therefore, the integral of dx over x squared plus 5x plus 6 is in fact equal to the integral. You see a was what? A was minus 1. So I've got minus 1 over x plus 3, right? b was 1, right? So plus 1 over x plus 2 dx. But those are integrals I can solve with a kind of trivial u substitution, right? I can use a u equals x plus 3 substitution, and I can use a u equals x plus 2 substitution to get natural logs there. So the answer is simply minus the natural log of the absolute value of x plus 3 plus the natural log of the absolute value of x plus 2. Right. Oh, I heard a plus c. Thank you. That's good. Any questions? Let me just take a second here to try to do this another way. Oh, I think I'm going to regret that. What would completing the square look like here? That's x plus 5 halves, right? Ooh, unpleasant. Squared. Then I have to subtract 25 fourths to be fair, right? So 6 is equal to what? 6 is equal to 24 over 24. Excuse me, not quite right. 24 fourths, right? Duh. So 24 fourths minus 25 fourths. Hey, that's actually not that bad. That's minus 1/4, right? Do you guys remember what? So this we could do with a what? You could make like a x plus 5 halves equals what? 1/2 what substitution? I have what pattern do I have? I've got like variable squared minus number squared. I'll make a secant substitution, you think? So you guys prefer a secant substitution? Is that right? Okay. I don't want to do that. I want to use like I'm going to use a hyperbolic function here. So if I use hyperbolic, I should do what? Coth, right? Yeah. So if I let this be 1/2 coth phi, right? Then, whoa, what on earth? Marker's alive. What's that? Oh, I don't know. These are options we have, like. Yeah, I mean, it's up to you, unless I say otherwise, yeah, that's right. So I would say, generically speaking, since you guys are more comfortable with trig functions, it's probably a safer route for most of you to try trig functions, but you know, if you do that, and then you find yourself face to face with like the integral of secant to the fifth or something, maybe you should rethink your choice. Let's see here. You know, certain trigonometric functions you just really don't want to integrate. And it is sometimes the case that once you find something like that, you might want another way out, and hyperbolics give us a way out. So that's minus 1/2 cosecant squared phi d phi, right? And the downstairs simplifies to what? Just 1/2, or 1/4, right? Rather 1/4 cosecant, hyperbolic cosecant squared phi. Now, those cancel, right? And we're just left with minus 1/8. Oh, I'm sorry. Stupid. Minus 2 phi plus a constant. In other words, minus 2 times what? The inverse hyperbolic cotangent of what? Yeah. Yeah. Now remember the derivative of coth and if I remember right, the derivative of coth and the derivative of inverse hyperbolic tangent are just off by minus. So I think I can also get away with just swapping out the minus for an inverse hyperbolic tangent. But it is interesting though, right? That this and that are the same answer. So I think if I write it in terms of the, I think I'm a little bit, I'm speculating a little bit here, guys, but I think this is also 2 inverse hyperbolic tangent of 2x plus 5 plus a constant. And if we go back to 7.9.2, we had relations between the natural logs and the inverse hyperbolic functions, remember? What was the relation of inverse hyperbolic tangent and natural log back in, oh, thanks.
I'm just going to leave it open because
Yeah, you're fine. The inverse hyperbolic tangent of x is 1/2 natural log 1 plus x over 1 minus x. Did I get it right? Or is this right? So if you look at inverse hyperbolic tangent of, what was it? Basically 2x plus 5, what's that look like? Which is what? Two x plus what? Yeah. Minus 2x what? Minus 4. Curious. I think in order to understand why these are equal, I have to get into the issues of where the domain is for the... Actually, I think this is only true for certain x, whereas this is true for what? So I think what's going on here, if I was to make a more detailed study of this, and I should do it someday for you guys, but the function we're integrating is what? It's you can graph it pretty easily from the partial fractions decomposition, right? It's got vertical asymptotes where and where. -3, right? And -2. Let's see, what's it look like? I need to plug in a point. Plug in 0, what do you get? It's positive, right? 1/6, so 0 is something like this. So that means it's doing this. I can tell from the initial expression it has no zeros. Is there any way you can get 1 over 5x squared plus, x squared plus 5x plus 6 to be 0? No, you cannot. This function has no real zeros. So the graph has to look something like, well, I guess the question is what happens in here. If I plug in like -2.5, what do I get? -2. What? -2, -4. I think it's negative. So unless I made a mistake, which is entirely possible, it's like this in here. And then I suspect it's like this over here. So what I kind of figure, guys, is this answer, the inverse hyperbolic tangent integral, it's probably only applicable to like one of these cases. My guess would be in here. Whereas this natural log integral is more robust. This works on any one of these disconnected regions as an integration, as an antiderivative to the given function. So maybe that's the downside of using something like this as your integral. I have a suspicion that this only works for a certain region, whereas this is applying more generally. But again, I'm speculating. I should work these things out. Anybody found a systematic discussion of this in the book somewhere? Probably not. I digress. All right.
In our notes, it says there's a 1 element of 1 plus x.
Mm-hmm.
1 minus x is, like that's for when x is between -1 and 1.
Right.
So I assume it'll like still be the same. Not -1 and 1. But
Right.
between-
Negative. Yeah, right. So what that would mean for this application, we would mean -1 less than 2x less than 2x plus 5, right? Less than 1, which would give us what? -6 less than 2x less than -4, divide by 2, -3 less than x less than -2. Like I was speculating, it's only here where I can compare this inverse hyperbolic tangent of 2x plus 5 with these guys. Because that expression, inverse hyperbolic tangent of 2x plus 5, is only defined in here. So yeah. So I know, at various points in my life, I've got more excited about these inverse hyperbolic functions because it seems like it's a way around partial fractions. You go back to chapter 7, this is a basic integral, right? Remember? Integral of a dx, what? dx over, x squared minus 1 is what? It's straight up inverse hyperbolic tangent of x plus a constant. Game over, end of story. But the fine print here is that's only good for what? For that, right? But this function is what? In fact, it's 1/2 of 1 over x plus 1 minus 1 over x minus 1, if I remember right. We can check me on that. Make a common denominator here, see if I guessed right. I get x minus 1 minus x plus 1. Oops. Swap that. Let's try it again. So if you make a common denominator, multiply this by x plus 1, x minus 1, so I get the x's cancel. 1 minus minus 1 gives me 2. 2 cancels with 2. That's a half. There you go. That's the partial fractions decomposition. So this dx over x squared minus 1 function, the 1 over x squared minus 1 function, it looks like, it's got asymptotes, vertical asymptotes at 1 and minus 1. Oops. Sorry. I don't know exactly what it looks like, but can you guys tell me? It's something like that again. Here, let me hedge my bets. It's either, I don't feel like doing arithmetic, it's either this shape, or it's, wait a minute, it can't be that. I wonder if that's right. I think this is supposed to be this, guys. It doesn't, let me go on here. I hope you have the idea. I'm getting off track here. I'm just really just making a comment that we can't just use the chapter 7 stuff without qualification, because the domain of the inverse hyperbolic functions is somewhat limited. All right? Whereas these sorts of expressions are more robust. That's all I was trying to say. All right, let's move on here. I have a couple more examples to show you. These will be a little bit more interesting. Let's try to find the partial fractions decomposition for 8 x cubed plus, 8x cubed minus 57 x squared plus 94x minus 41, all divided by x minus 4 times x minus 3 times x squared minus 2x plus 5. I need to create a homework problem about all this. I didn't get around to it this semester, though. I know you're sad. Am I right? No? It's too early? Sorry. No. Don't worry, guys. I'm too busy to make new homework problems. You're safe. At least for this course. I do have to make homework problems for other courses, but thankfully you guys have this thing called a book, and it has some pretty nice problems in it. All right, so goodness gracious, what to do here? Well, this, folks, is what? This is x minus 1 quantity squared plus what? Yeah, plus 4. So that we can't factor over the reals. It's irreducible. It's a prime quadratic. All right. So then, here we go. Off we go. So we do a over x minus 4 plus b over x minus 3 plus c plus d times x minus 1 over x, well, I could write it as, I'll write it as x minus 1 squared plus 4, but you could just as well write that as, of course, x squared minus 2x plus 5. But there you go. Now all we got to do is find a, b, c, and d, and then we'll have found the partial fractions decomposition, which then means, of course, we could integrate this thing if we wanted to, right? So what's our next step? Just like with my first example, before I got distracted with hyperbolic nonsense. Right? So we multiply by the denominator both sides. What's that give us? That brings us to 8x cubed minus 57x squared plus 94x. All I'm doing is copying down the numerator, right? And then here's where I got to think a little bit. So first of all, I have got a times x minus 3 times, I'm just going to write it as x squared plus minus 2x plus 5 because it's easier to write that. All right. Then plus b times what? So the x minus 4 canceled with the a term. Let's see here. Next I would get b times x minus 4. The x minus 3 canceled, and then the quadratic term. And then I get what? Plus what? plus c plus d times x minus 1 times what? This time the quadratic term cancels, right? And we just are left with x minus 4 and x minus 3 here. Let me call this monstrosity star. Okay? So what do we do? I mean, there's some very low-hanging fruit here. We can use the idea we used in the last example to pick off some easy things. Like if I put x equals to 3, or if I put x equals to 4, I get some really nice equations, right? For example, if I take star and I put x equals to 3, what do I obtain? I get 8 times what? Times 27 minus 57 times 9 plus 94 times 3 minus 41. I think really nice might have been a slight exaggeration. But we get something that's manageable. What makes it nice is that there's, that's gone, and that's gone. All we're left with is b times 3 minus 4 times what? Times 9 minus 6 plus 5. And this implies that b is equal to what do you think? I mean, it's just a matter of crunching the numbers, right? You do that, I think you should get minus 5. Would it make you feel better if I punched numbers in a calculator? It'd make me feel slightly better, because if I made a mistake somewhere else, we'd find it now. So for the left-hand side, I get minus 56. What? Oh, man. For the right-hand side, I get what? If you agree with me, I mean, if you disagree with me, so I get minus 8b over here, right? Oh, 7?
No, the negative right there, but then when you solve,
Oh.
b is going to equal 7.
Oh, okay. Cool. Okay, so I have misread my my solution. Good. All right. You feel better? I feel better. All right, how about x equals to 4? We got what? We got 8 times 64 minus 57 times 4 plus 94 times 4 minus 41 equals what? Oh, thank you, yes. Be careful. And then over on this side, everything goes away except for what? A times what? Times 4 minus 3 times 16 minus 8 plus 5. This tells me A is equal to what? So I get minus 65 on this side, and over here I get (13). Therefore, A is equal to minus 5. All right. So we still got 2 more constants to go, right? So how do you solve this sort of thing? This equation, this star has to be true for all x, actually, we can argue. So the easiest thing to do, I think at this point, I mean, you can just plug in values if you want. I don't recommend that. Or what's perhaps easier is to equate coefficients of like terms. So like I can collect, for example, all of the terms here with an x cubed. What are those going to be? 8 equals what? So there's an 8 here. Where are the x cubed terms here? Just there's an a, right? How many x cubes here? Plus b. Where else do we get x cubed? Right. Plus d. So there's an equation. Oh, but hey, we know a and b, right? What's that say d is equal to? D is equal to 8 minus a minus b, which is what? 8 plus 5 minus 7, which is what? 6. So apparently d is equal to 6. And then let's see here. What else can you do? We could look at the squared terms in star, right? What would that give us? I've got a minus 57. How else can I get a square? How about a? But what's another way you can get a square from here? Oh, I'm sorry. I shouldn't say a. I should say what? Not a, but minus 3a, right? Because minus 3x squared gets an a. Where else can you get x from? How about this? Minus 2x squared, so I'm minus 2a. Is there any other way I can get an x squared from multiplying this? I don't think so. How about over here? This gives me a minus 4b. And also minus 2b. Over here, that's it for this. There's no other x squared terms. Yeah, it's probably helpful here if I multiply this back out. This is x squared. Multiply it out for the first time. Minus 7x, right? Plus 12. So you got, like you said, plus c, right? Then what? Minus 7d, right? Plus d, where'd you get the plus d from? Oh, right, so that's just a minus d maybe? Why is it plus d? I think it'd be minus d. I get the 7. Oh, you're saying it's plus 70?
No, you have negative 7d, but then
Oh, yet another plus d, you say? Let me just multiply it out since we're having trouble seeing it. C plus dx minus d times x squared minus 7x plus 12, right? What's that equal? Let's just keep x squared terms. We get minus dx squared, right? This times that, and what else? Minus 7 dx squared. Is there any other way to get an x squared from these sorts of things? I mean, there's 9 terms, but these are the only ones that have x squared in them, right? And that's why I said minus d. Oh, so c equals what? 8. All right. Okay, guys, so next class, obviously I'm out of time with you guys, but I had another example linked together with this one. So in the next class, I'm going to do this example. If you have some time, you might try it out for yourself. 3 minus, oh, sorry, writing the answer. Don't write the answer. This one, 3x squared minus 12x plus 21 over x minus 2 cubed. So for this one, you're going to try something like a over x minus 2 plus b over x minus 2 squared plus c over x minus 2 cubed. Let's see how that goes. Sorry, I got distracted with the hyperbolic stuff with you guys. Anyway, I'll see you tomorrow.